Dear students, in this video, we discuss about the Navier-Stokes equation. In Navier-Stokes equation, we know from the theory of fluid dynamics, the equation of continuity, the equation of conservation of mass, and the equation of motion, which is known as also Navier-Stokes equation, is the conservation of momentum. So the Navier-Stokes equation of motion is the conservation of momentum. To prove it, let us consider a rectangular parallel pipe, which is shown in diagram, with one corner at D and with the center XYZ, and sides are parallel to the axis and of the length delta x, delta y and delta z respectively, which is also shown in figure. Now component of the stress on the surface x is equal to 0, means the surface CD, C dash, D dash, and on the opposite surface x plus delta x is equal to 0. The component of the surface AB, B dash, A dash are P dash x, P dash y, P dash z dash respectively. Now from Px is equal to P into xyz and P dash x is equal to Fx plus delta x into y into delta y into z. So P dash x is equal to Fxyz plus delta by delta x into Fxyz into delta x. Similarly, so P dash x is equal to Pxx plus delta Pxx upon delta x into delta side length delta x. So P dash x minus Pxx is equal to delta Pxx upon delta x into side length delta x. Similarly, P dash yx minus Pxy is equal to delta Pxy upon delta x into delta x. Similarly, P dash xz minus Pxz is equal to delta Pxz upon delta x into delta x. This is our equation number 1. Now component of stress are per unit area. Similarly, on the surface y is equal to 0 and y plus delta y is equal to 0 are. Then we get P dash yx minus Pyx is equal to delta Pyx upon delta y into side length delta y. P dash yy minus Pyy is equal to delta Pyy upon delta y into side length delta y. P dash yz minus Pyz is equal to delta Pyz upon delta y into side length delta y. This is our equation number 2. Similarly, for the surface z is equal to 0 and z plus delta z is equal to 0. The component of stress are P dash zx minus Pzx is equal to delta Pzx upon delta z into side length delta z. P dash zy minus Pzy is equal to delta Pzy upon delta z into delta side length delta z. P dash zz minus Pzz is equal to delta Pzz upon delta z into delta z. This is our equation number 3. Now if you let capital X, capital Y, capital Z be the component of external forces F per unit mass, and Ax, Ay and Az be the component of acceleration, and rho is the density, then the velocity of the equation of motion by Newton's second law, that the rate of change of linear momentum is equal to total force. So rho delta x delta y delta z into Ax is equal to x into rho delta x delta y delta z plus P dash x delta y delta z minus Pxx delta y delta z plus P dash xy delta x delta z minus Pxy delta x delta z plus P dash x delta x delta y minus Pxz delta x delta y. This is our equation. Then Ax into rho delta x delta y delta z is equal to capital X into delta x delta y delta z rho plus P dash xx minus Pxx delta x delta y delta z plus P dash xy minus Pxy delta x delta y delta z plus P dash xz minus Pxz delta x delta y delta z. Now using equation 1, 2 and 3, then we get Ax is equal to capital X plus 1 upon rho delta Pxx upon delta x plus delta Pxy upon delta y plus delta Pxz upon delta z. This is our equation number 4, where capital X, capital Y and capital Z are the component of external forces per unit area. Now we know that from the relation of viscous stress tension strain rate of strain tensor, Pij is equal to twice mu Tij minus P plus 2 by 3 mu divergence of Q into delta Ij. So Pxx is equal to twice mu Txx minus P plus 2 by 3 mu divergence of Q. Pxx is equal to twice mu into A minus P plus 2 by 3 mu divergence of Q. So Pxx is equal to twice mu into delta U by delta x minus P plus 2 by 3 mu divergence of Q. This is our equation number 5. Similarly, Pxy is equal to twice mu Txy is equal to Pxy is equal to twice mu into H. Pxy is equal to mu into delta U by delta y plus delta V by delta x. This is our equation number 6. And Pxz is equal to twice mu Txz and equal to Pxz is equal to twice mu Txz. Pxz is equal to twice mu into G. Pxz is equal to mu delta W by delta x plus delta U by delta Z. This is our equation number 7. So putting value 5, 6, 6 and 7 in equation number 4, then Ax is equal to capital X plus 1 by rho into 2 del by del x mu del u by del x minus delta p by delta x minus 2 delta by delta x of 2 by 3 mu divergence of q plus delta by delta into mu delta u by delta y plus delta v by delta x plus delta by delta z of mu into delta w by delta x plus delta u by delta z. If viscosity is variable, if we take viscosity is constant, then Ax is equal to capital X plus 1 by rho minus delta P by delta X plus 2 delta by delta X plus this. So the result is valid when the value mu is variable. Similarly, we can obtain Ax, Y and Az. These three relations gives next equation motion when viscosity is variable. If viscosity is assumed to be constant, then the equation 6 is become delta px is upon delta x is equal to del twice mu into del square u by del x square minus del p by del x minus 2 by 3 mu del by del x of divergence of q. This is equation number 9. Similarly, delta p by x upon delta y is equal to mu into delta by delta y of delta u by delta y plus delta v by delta x. This is our equation number 10. Delta p zx upon delta z equal to mu into delta by delta z of delta w by delta x plus delta u by. This is our equation number 11. So adding 9, 10 and 11, then we get this is equal to twice mu del square u by del x square minus del p by del x minus 2 by 3 mu del by del x of divergence of q plus mu del by del y of del u by del y plus del v by del x plus mu del by del z of del w by del x plus del u by del z. This is equal to, then we solving it, then we get this is equal to minus delta p by delta x plus mu del square u by del x square plus del square u by del y square plus del square u by del z square plus mu by 3 into delta by delta x of divergence of q. So put value in equation 4, then we get Ax is equal to x plus 1 by rho minus delta p by delta x plus mu nebula square u plus mu by 3 delta by delta x of divergence of q, or Ax is equal to x minus 1 by rho delta p by delta x plus nu nebula square u plus 1 by 3 nu del by del x of divergence of q, where nu is the kinematic viscosity. And we can also be note d by dt is instant for material derivative, and material derivative d by dt is equal to delta by delta t plus u del by del x plus v del by del y plus w del by del z. Similarly, d by dt of u is equal to delta u by delta dy plus delta u by delta t plus u del u by del x plus v del u by del y plus w del u by del z. या ax is equal to x minus 1 by rho del p by del x plus nu nebula square u plus 1 by 3 mu del by del x of divergence of q. Ay is equal to y minus 1 beta rho del p by del y plus nu del square v plus 1 by 3 nu del by del y of divergence of q. Z is equal to z minus 1 by rho del p by del z is equal to nu plus del square w plus 1 by 3 nu del by del x of divergence of q. So for the incompressible fluid, the equation of continuity divergence of q is equal to 0. Yeah, del u by del x plus del v by del y plus del w by del z is equal to 0. So our equation 12 will become Ax is equal to du by dt, is where d by dt stand for material derivative is equal to x minus 1 by rho del pi by del x plus nu nebula square u. Ay is equal to y minus 1 by rho del p by del y plus nu nebula square v. Az is equal to z minus 1 by rho delta p by delta by nu nebula square w. So the equation 3 is known as Navier-Stokes motion for compressible fluid, and in tensor notation this can be written as dq by dt is equal to f minus 1 by rho gradient of p plus nebula square of q. This is our equation results, and solving we get the result.